Hello everyone, this is Mrs. Lindsay. We are on part 3 of probability. Today we are going to be talking about conditional probability and independence, and this is in section 11.3, again in the MHH second half of the textbook. Okay, so conditional probability. What is it? Well, sometimes the occurrence of one event affects the probabilities of other events. When this is the case, we say that one probability is conditional upon the other. When the occurrence of an event A does not affect the probability of event B occurring, we say that the events are independent of each other. So for example, two cards are drawn without replacement. So the key there is without replacement from a deck of standard cards. Okay, so again, if you don't know the standard deck of cards, please take a moment, look that up. I will assume that you know what that is, okay? Find the probability that the second is a heart, given that the first is a heart, and two hearts, so in other words, two hearts are drawn. Okay, so, solution. Recall the standard deck of cards, again, has 4 suits, hearts, diamonds, spades, clubs, consisting of 13 in each for a total of 52 cards. So you've got your ace, 2 through 10, jack, queen, king. Oops, sorry about that. Okay, so one card has been drawn without replacement, so there are 51 cards remaining. The first card is a heart. Then there's 12 of them remaining, because again, there's 13 in each suit. Thus, the probability of getting a heart on the second card is 12 out of 51. So, drawing 2 cards in succession would be 52 times 51, but getting 2 hearts in succession would be 13 times 12. So the probability of getting 2 hearts in a row would be 12 times 13, 13 times 12 in the numerator, and then the denominator would be 52 times 51. Okay, so the way we could actually mathematically write it here is probability of getting the heart first times the probability of getting the heart second, given that we already know the first one is a heart. Okay, so definition, let A and B be events in the sample space. Then the probability that A occurs, given that the probability B occurs, is a conditional probability. So probability of A slash B. So the probability of A and B divided by the probability of B. Okay, so there's a little bit of reasoning here. We know for certain that B occurs, therefore the only possible outcomes are those in B. Thus we can shrink or shrunk the sample size down to B. So if A also occurs, then we see that both A and B occur. Okay, so that's kind of the rationale behind that. All right, so here's an example. We actually did this a couple weeks ago here. This is our example with males and females talking about drinking coffee, what they prefer and not prefer. Sorry about that. The findings are summarized again below. So we want to find 2 different probabilities. What is the probability that a randomly selected student A does not drink coffee, given that he is male, and B is female, given she prefers regular coffee? Okay, so let's take a look here at our solution to that. There are a total of 260 males, again looking here at our chart. Of these, exactly 18 do not drink coffee. Thus the probability that does not drink coffee, given that they're male, is 18 out of 260, which is again is 0.069. So again, hopefully you see where those are coming from in our chart. 18 do not drink coffee out of 260 males. So here's where we're looking here, 18 out of 260. Okay. Next part, B, is female, given that she prefers regular coffee. 341 individuals who prefer regular coffee, and of those, exactly 145 are female. Thus, probably it's female that, given that they prefer regular coffee, is coffee is 145 over 341, which is 0.425. Okay, so let's try another example here. Here we have a table, shows smoking habits of asthma sufferers. So we have men and women, non-smoker, light smoker, heavy smoker, and then our totals. So the first part here says, find the probability that a randomly selected individual is a woman, given that she is a light smoker. So in this case here, given that she is a light smoker, so total of 149 light smokers, but we want to know what's probably that this individual is a woman. Well, there's 87 of those are women. So 87 out of 149. And again, if you want to leave as a fraction, you want to go convert that to a decimal or a percent, either way is fine. I'm going to go ahead and just leave those right now as a fraction. Okay, so next, what percentage of heavy smokers are men? Well, in this case, it's not worded the same as A, but it's given they're heavy smokers. So the heavy smokers, there's 145 of them. We want to know that they are male, and 80 of those are male. So 80 out of 145. So again, the given is in the denominator, right? And in the numerator is both of them are occur. So it'd be a male who is a heavy smoker. So C, find the probability that, sorry, my phone was going off. Find the probability that a randomly selected individual is a non-smoker, given that she is a woman. Okay, so given woman, so there's 464. And now we want to know the individual is a non-smoker. So out of those, we would have 312. So this is where I'm looking here, 312. All right, so let's try another example. So again, here we have another chart. Group of students were asked if they carry a credit card. The responses are listed again below. Freshmen and sophomores carry a credit card, don't carry a credit card. Again, totals. So take a minute, pause this video, try A, B, and C, and then push play when you are ready to check your answers. Okay, so taking a look here, hopefully these make sense. Please notice I did actually reduce these fractions. I don't typically care if you again write it as a fraction, a decimal, or a percent, but I would say go ahead and reduce those fractions if you could. So the first one is find the probability that a randomly selected student owns a credit card, given that he is a freshman. So given that they're a freshman, there's 60 of them. And again, we want to know that this person owns a credit card, so that would be 10. Okay. So in this one, find the probability that a randomly selected student is a freshman, given that she owns a credit card. So again, they reverse it. The given here in this case, let me pull up my pen and hopefully it doesn't switch pages on me. So now it's given credit card. Okay, so now it's 30 is the total. Now we want to know that that person is a freshman, which would be 10. So 10 would be the numerator over 30. And C, find the probability that a randomly selected student is a sophomore, given that he or she does not own a credit card. So not owning a credit card. Now we're looking here at the 70. Now we want to know is that individual a sophomore, and that's the 20. Okay, so again, one of the most important features of the definition of conditional probability above is that it gives us a formula for the probability that two events both occur. Okay, this is useful for computing probabilities using given conditional probabilities. Okay, so again, two events occur. All right, so an example here. A test for a disease reports negative 0.02% of the time for people who are infected with the disease, and reports negative 82% of the time for people who are not infected. Okay? It is known that in a certain community, 8% of the residents are infected with the disease. Okay, so let's kind of talk about this a little bit. I'm actually going to jump ahead a couple slides here because I think it's a little bit helpful. We'll come back to the problem set there in a minute. We're going to let D denote the event the person is infected with the disease. U denote the event the person is not infected. N be the event that person tests negative. So what I just read to you, written out in terms of what we denoted here, probability that the person is infected with the disease is 0.08. Probability that the person tests negative given the person is not infected. And then this is the probability of the person tests negative given that the person is infected with the disease. Okay, so I'm just talking about these three right here. So again, if we go back to this portion right here is the probability that the person tests negative given that the person is infected with the disease. Here is the probability, let me write this down first, that the person, given the person is not, let me repeat that. Probability that the person tests negative given that the person is not infected. And this one is the probability that the person is infected with the disease. Okay, so let's go over to these examples here real quick. What is the probability that a randomly selected citizen tests negative? B, what is the probability of a false positive? That is, what is the probability that the person tests positive even though they do not have the disease? C, if a person tests negative, what is the probability that they are not infected? Okay, so again, this is how we kind of denoted these. All right, hopefully this makes sense here at the bottom. So D is, again, probability that a person is infected with the disease. So U, right, is the probability that the person is not infected, would be 0.92. So it would be the opposite of probability of D. So let's look at A. To find the probability that a person tests negative, we consider these two possibilities. Either the person tests negative and is not infected, or they test negative and is infected. So we actually have two scenarios here. So the first one, and then our second one here. So test negative and is not infected, probability of N given and D, and the test negative and is infected, probably N and U. So again, by our conditional probabilities, that'd be the probability of D times the probability that N given D. So probability of D is 0.08. Probability of N given D is 0.0002. Okay. Plus probability of U times the probability of N given U. I'm missing a parenthesis there. Fill those in, multiply, add, put those in your calculator. That would be 0.75. So about 75% there. So again, this right here is coming from our conditional probability that we had 2 or 3 slides back. All right, B, of people who are uninfected, 82% test negative. Thus, the remaining 18% must test positive. So the probability they test positive given they're uninfected is 0.18. C, now in this one, this was if a person tests negative, what is the probability they are not infected? Okay, so again, if a person tests negative, what is the probability they are not infected? So in the denominator, the probability that the person tests negative is that 0.754416 over, and then the numerator, probability of U times the probability of N given U is 0.92 times 0.82. So that is, if a person tests negative, it's almost a certainty that they are uninfected. Okay. All right, independence. Another little important portion here. Two events are said to be independent if the probability of one occurring is unaffected by the occurrence of the other. So A and B are independent if and only if the probability A equals the probability A given B. So, as we've talked about before, probability A and B both occur is the probability of B times the probability A given B. If the events of A and B are independent, we can substitute probability A in place of probability A given B to get the following. So probability A times the probability of B. So again, that is if they are independent of each other. Nothing affects the probabilities from one to the other. This can happen in a couple ways here. If we know that two events are dependent, we can use the theorem to find the probability that both events occur. If we know the probabilities, we can use the formula to check whether or not the events are independent. Example, two successive tosses of a die are independent of each other. Okay, so if I roll, in this case we're asking 3 and 4. It doesn't matter what I roll the first time, it has zero effect on what I roll the second time. So if I wanted to roll a 3 and a 3 or a 1 and a 2, it has zero effect what I roll the first time versus what I roll the second time. So the probability of rolling a 3 and a 4 is literally the probability of 3 times the probability of 4. So this is our solution right here. So the probability of rolling a 3 is 1/6, probability of rolling a 4 is also 1/6, and multiply those together. So kind of just to sum that up again. If we draw 2 cards in succession, okay, if we draw 2 cards without replacement, they are dependent on each other. The probability of drawing an ace on the second draw clearly depends upon which card was drawn first. However, if we put it back, by replacing the cards, the deck doesn't change from the first draw to the second draw. So again, there is no change there, and they are independent of each other. So hopefully that makes sense. Because if you take something out, you've changed your entire group and subset. Here I put it all back in, so each time I'm dealing with an entire 52 card deck, first draw and second draw. So kind of as a rule here, selection with replacement will produce lists in which each entry is independent of each other. Okay, so let's go back to our coffee drinking scenario here. So again, earlier we did a couple weeks ago, and we just did it a little earlier too. Determine whether coffee preference and gender are independent. Okay, so if the categories are independent, then we would have the probability of being female equals the probability that they're female given that they prefer regular coffee. So from our previous example, okay, we actually did this a while ago here, we got that to be 0.425. On the other hand, of being probability that they're female is 273 over 479. So total of females over total just number within the chart. So that's 0.477. Since they are not equal, gender and coffee preference are not independent, and female students are more likely to prefer regular coffee. So again, here we're comparing probabilities to show whether or not something's independent. Okay, so let's talk about a little famous problem here, the birthday problem. Suppose we have a group of n people. What is the probability that at least 2 of them share the same birthday? Also, how large of a group do we need for this probability to exceed 50%? Okay, so the key is, are birthdays independent? And yes, they are. Birthdays of different individuals are independent of each other, and also the probability at least 1 duplication means the probability is equal to 1 minus probability of no duplicates. Okay, so let's just pick a number here. So let's say that there's 3. Probability that there are duplicates equals 1 minus the probability that there aren't. Okay, so we do 1 minus 364 over 365. So there's 365 days, all right, in the year. 364 options. Take 1 away, so that's times 363 over 365. So that's 0.008. Well, what if there's 4? Okay, if you notice, exact same thing as 3, but we added the extra portion here of 362 over 365. So again, we're kind of taking out the date so there's no duplicates. If we kind of keep going in this trend, the probability keeps increasing. Okay, so you can see from this one here, 0.016 increased, right? Keep going, 5, 6, 7, 8. So when we get to 23, the probability is around 0.507, so about 23, 22 I believe is a little bit under, so when you get to 23, that is when it's like 50%. Okay. Another example here. Among the last 1 million live births recorded by the State Registry of Births, there were 513,000 males and 487,000 females. Suppose we pull 5 birth records at random from this bank, selecting records without replacing. So again, that's always important to know if you're replacing or not. Again, sorry about that. Always kind of switches on me. Without replacement. Find the probability that all 5 are female, none are female, exactly 2 are female, at least 1 is female. Okay. Well, let's think about this a little bit. We could do this by counting. However, it's definitely a little bit easier to use the idea of independence here. Even though we're drawing without replacement, there is probably no harm in treating the successive draws as independent of one another, because we are selecting such a small sample, only 5 records from a large collection of 1 million births. The likelihood of the same record being pulled twice is very, very low. Okay. Okay, so the probability is a randomly chosen birth record is male or female. Okay, so the probability that it's male, 513,000 over 1 million, 0.513. Females, 0.487. Okay, that's going to be useful for us. So, the first one, okay, all 5 are female. So basically on this one, we're really just going to take the probability of first female times the probability of second female, all the way up to the probability of being fifth female, and those probabilities are all the same of 0.487. So we're going to multiply that together 5 times, or raise it to the fifth, so we get that to be 0.0274. Similarly, the probability that all 5 are male, so again we do the same sort of idea, but now instead of doing female, we're doing a probability first one's male times the probability first one's second one's male, and again those all have the same probabilities, so times each other 5 times, or raise to the fifth, which is 0.0355. The third portion, which says find the probability that exactly 2 of the records are female, we have to think of outcomes as a sequence of like 5 letters. So M being male, F being female. This, we have to use combinations because we don't necessarily care when the females are drawn. If it's the first 2 or the last 2 or somewhere in the middle. So we have to do 5 choose 2, which equals 10. Okay, notice that's where we're getting this number down here from. And we must choose 2 slots out of the 5 in which to place the females. The remaining 3 will be males. Okay, so the probability of any such sequence will be 0.487. So if you recall again, that is the probability being female. We need 2 of them. And then this is the probability being male. We need 3 of them. It's 0.032. So again, this is what we're looking for. But again, order doesn't matter, so we got to multiply those 2 together. So that gives us a total probability of 0.32. Okay. And the last one is the probability that at least 1 is female. Well, if it's at least 1 female, we can do 1 minus the probability of all males, which we found earlier. So that would be 0.9645. Okay, and this wraps up our 3rd day working with conditional probability and independence.